Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my 6th lecture under the first module of DC generators. In the first lecture, we have seen the construction details of DC generator. In the second lecture, we have seen the working principle of DC generator and how commutator is playing an important role in the working of DC generator. In the third lecture, we derived the expression for EMF equation of DC generator. In my fourth lecture, we have discussed the various types of DC generator. And in the fifth lecture, we have solved some of the tutorials based on the concept discussed in the previous 4 lectures. In today's lecture, we are going to see the concept of armature reaction. So what is an armature reaction? So we know that in a DC machine, the magnetic flux is only due to main poles, and that we refer to as main flux. So when current starts flowing through armature conductors, it also creates a magnetic flux, and that we call at armature flux. So this actually distorts or weakens the main flux. So this effect we call it as armature reaction. So we can define armature reaction as the effect of magnetic flux set up by armature current on the distribution of flux under the main poles of generator. So here let us consider first case that only the main flux distribution we are considering. So in the meanwhile, we are not considering the effect of armature. Here in first case, we are only considering the distribution of main flux only. So here we are assuming that the armature is rotating in clockwise direction. For our simplicity, we are considering only 2 poles, and when the field winding is energized, the generator is not connected to any load. And this is how my field flux distribution is like. So you can see that the field distribution is uniform. There is no disturbance in the distribution of main flux. Okay, so the observations that we can conclude from this is, as I told you earlier, flux is uniformly distributed with respect to d-axis, direct axis. Here we have GNA and MNA, where GNA is called geometric neutral axis and MNA is called magnetic neutral axis. Both are coinciding with each other. So what is GNA? It is nothing but the line passing through midway between any 2 magnetic poles. We call it as geometric neutral axis, or simply GNA. The axis along which there is no EMF induced in armature conductors, we call it as magnetic neutral axis, or simply MNA. Okay, and the vectors that are shown represent the MMF produced, MMF that producing main flux both in magnitude as well as direction. So when I take you to my previous slide, here you can see, so GNA and MNA both are coinciding with one another, and you can see this is the resultant flux direction and the main flux direction. In this case are both in the same direction. Second case, I'll assume only the distribution of armature flux only. So assuming that the main flux or the main field coils are not excited, so the distribution here is showing only the armature flux distribution. So we can see that the armature is connected to the load, and on one side of the armature you have cross indicated, and the other side of the armature you have dot indicated. Okay, so one should remember that dot and cross are the current entry or leaving indications. So if the current is going into the plane or into the board, that we indicate as cross. If the current is coming out of the board or out of the plane, we indicate by dot. Okay, and flux, that is, you can see the purple lines that are shown around the conductors. These are the magnetic field direction around the armature conductors, and that can be given by right hand thumb rule, where thumb indicates the current direction and the curled finger indicates the magnetic flux or magnetic field direction. Okay, so this is how is the distribution of armature flux only will look like. So the resultant flux in the armature, as you can see clearly, will be towards down. Okay, so because here as you can see, in the entire armature the flux direction is always downwards. Okay, so that is why the resultant vector of armature flux and the resultant flux are downwards. But truly speaking, both cases will never exist independently, isn't it? So both happen simultaneously. So when the field is excited as well as the armature is loaded, so both will exist. By both I mean main flux as well as armature flux, both will exist simultaneously, and this is how my resultant flux will be. Okay, so the as you can see clearly, the pink lines are the main flux and the purple lines are the armature flux. Okay, so both happen simultaneously in my DC machine. Okay, so here you can see, if you can observe carefully, here the direction of in this area, you can see the direction of main flux as well as the armature flux are same. When I consider this area, the direction of armature flux and the main flux are opposing to each other. When I consider this area, here also the armature flux and the main flux both are opposing, not opposing, both are in the same direction. And here again, if I consider both the fluxes, here both the fluxes will be opposing to each other. Okay, so as you can see here, among the four areas, two areas we can see the both fluxes are aiding each other, and remaining two areas fluxes are opposing each other. So that is why here both fluxes are getting strengthened, and here also both fluxes are getting strengthened as both are in same direction. In these two areas the resultant flux get weakened because both fluxes are in opposite direction. Okay, so this is how you can we can analyze or observe the combined effect of both fluxes. Okay, so if I go to my previous slide, you can see here, let me clear the slide once. So for every pole there will be two tips. Okay, so in this case this is called trailing pole tip and this is called leading pole tip. Okay, so when the armature is in rotation, so whichever tip comes across first, that we call it as leading pole tip, and whichever end is coming later, that we call it as trailing pole tip. So when the armature is rotating, this end will come first, or this pole tip will come first, that is why it is called leading pole tip, and this pole tip will come later, so that is why it is called trailing pole tip. If I consider this pole tip, while the armature is rotating, that pole tip will come first under south pole, so it is leading pole tip, and for this pole tip under south pole it will come later, hence it is called trailing pole tip. Okay, so we can say that at trailing pole tips my flux is getting strengthened, and in the leading pole tips, my strength is getting weakened. Okay. So as a result of these two fluxes getting interacted with one another, this is my resultant flux distribution. Okay. So you can clearly see, because of both fluxes getting strengthened, the area or the fluxes both aid each other. That is why we can see the flux amount of flux is more crowded near these two areas, and in the remaining two areas, since both fluxes are opposing each other, the flux is not crowded, and it is less crowded when compared to the remaining pole tips. Okay, so what happens here is the MNA, as you can see, because of the interaction of both the fluxes, the MNA axis has been shifted. So this is the new MNA axis. Here no longer both GNA and MNA are coinciding with each other, because you can see from the phasor diagram, this is the main flux distribution, this is the armature flux distribution, and due to interaction of these two fluxes, this is my resultant flux. My MNA should always be perpendicular to my resultant flux. The angle between the resultant flux and the MNA axis should always be 90 degrees. Okay, so as I already told you, the flux distribution is no longer uniform and symmetrical. At the trailing pole tips, flux is crowded. At the leading pole tips, flux is weakened. And MNA is always perpendicular to the resultant MMF, as I have told you. Here the the new MNA is getting shifted through some angle theta. So because of this shift theta, the armature conductors and armature current gets redistributed as shown. Okay, so previously, since both were coinciding with each other, towards left I had cross and towards right I had dot. Since the MNA axis has been shifted through some angle, the current distribution as well as the MMF distribution will change accordingly as shown in the figure. Okay, so these are the various conclusions that we can get from the armature reaction effect, and that, as I already told you, some of the conductors, armature conductors, which were under the influence of south pole, now they will come under the influence of north pole, and vice versa also, due to the redistribution of armature conductors. So this is the concept of armature reaction in DC generator. This ends today's lecture on armature reaction. So in my next lecture, we are going to see what are the various effects of armature reaction and probably remedies of the armature reaction in DC generator. Until then, take care. Thank you. Goodbye.